So welcome to the second London Learning Lean seminar. Next week we have Amelia Livingston talking about group cohomology. But this week we're very pleased to welcome Chris Birkbeck from a Heilbronn Fellow at UCL, who's going to tell us about his work on modular forms.
Great. Well, thanks very much for the invitation. It's a pleasure to speak at this new seminar. As Kevin said, I'm going to talk about some work I've been doing in formalizing modular forms, Eisenstein series, and then for fun, trying to do this modularity conjecture at the end. Just start by saying this.
You're gonna prove it?
No, not yet.
Oh, okay.
I should start by saying that this is an area that's quite new to me. So a lot of this wouldn't have been done without help of a lot of people. So especially people on the Zulip chat, but I'm sure I'm forgetting people, but people like Alex Best, Ricardo, Kevin. Kevin's the first one that introduced me to Lean and all of this, and he suggested working with modular forms. But also other people like Yuri, Alex, Heather, and Mark have all been super helpful in either explaining how to formalize some bits of maths or like highlighting useful results which are already in the library. So it's kind of been useful without these people and lots of others I'm sure I'm forgetting. And also I should note that some of this stuff was technically already done to some degree in something which was given to Kevin. Kevin had a 50th birthday and he got given a present as part of this. And part of this, they gave him lots of different mathematical definitions. And one of those things was a basic definition of a modular form. And when I first saw this, that code wasn't quite working, but in getting it working again, because it hadn't been added to MATLAB, is how I learned to do Lean. So maybe that's not the best way to do Lean, but that it was very instructive to me to understand how that worked in doing this. And I think this was done by Scott Morris and a bunch of other people that are in this group. And I think I have a link that I can show you where you can find all the details if you're interested. Okay, so that all said, what I'm going to talk about today is defining modular forms and how to use them. So the first thing is some motivation as to what is modular forms, what are they, and why do we care? So in maths, we've cared about things like Differentiable equations for a very long time, and this is usually our source for motivating all sorts of things in number theory. And it's because you can state these questions quite easily, but they can be very hard to solve. And the best example of this is Fermat's last theorem, which you can see on the screen. It asks for solutions to x to the n plus y to the n equals z to the n, when you want x, y, and z all to be integers, and you want n to be at least 3. And you don't want the trivial solution, so you put this condition that x, y, and z, none of them are 0. And this is called Fermat's last theorem. And in order to solve this, we needed to create a whole bunch of new machinery to do this. And it's not a very easy question to solve, although we have done it, but it really relies on linking lots of different bits of mathematics, like areas from algebra and analysis together with geometry. And in general, solving differential equations is a very hard thing to do. So we want to look at some cases where we can actually do this, and this is where modular forms can help. And as I sort of mentioned, these modular forms come for the rescue because they allow us to create this link between the land of algebra and geometry, where these differential equations live, to the world of analysis. And this is a quite powerful statement. And to talk a bit more precisely, this link goes via the following. On the geometric side, you don't have Fermat's last theorem equation, but you have things called elliptic curves. These are geometric objects, describe a solution to the equations like the one here on the screen, y squared equals a cubic. You can take a and b to be rational numbers if you want. And if you were to plot this into complex numbers, you get a donut, which is why I've drawn a donut. Elliptic curves are hugely interesting. They have very interesting Galois representations and things attached to them. On the other hand, we have something in the analytic world, which are these modular forms, which these are complex holomorphic functions. These are special functions, and I'll define them properly in a minute. But they have Fourier expansions, which is what I've drawn here. Here, Q, or sometimes called a Q expansion. Here, Q stands for e to the 2 pi z. And these coefficients, these AIs of your modular form, these Fourier coefficients, they're the ones that capture all of the important arithmetic information. So what the modularity conjecture says, and one version of it, which I'll state later, is that if you had an elliptic curve, then you can find a modular form such that its coefficients know something about your elliptic curve. Specifically, it'll know how many solutions your elliptic curve has if you reduced it modulo some primes, if you worked over a finite field. And this close link between the two things is quite powerful because on the analytic side, we can do things which we can't really easily do on the elliptic side. And you might be asking, say, okay, this is great, but how do I use this to solve Fermat's last theorem? Well, roughly the idea is as follows. You assume that you had a non-trivial solution to Fermat's last theorem. So you had a non-trivial x, y, and z such that x to the n plus y to the n equals z to the n, n being at least 3. Then from this, you can construct an elliptic curve. And it turns out that this is a very special elliptic curve. It has some very interesting properties. And it turns out it's actually too special and too interesting. But it's hard to prove this. So you look at this thing and so you think, okay, well, let me get on my modularity train, go over to the modular form side, and attached to this elliptic curve, there should be some modular form that knows about it. And you go over to the other side and you figure out that attached to this elliptic curve, when you get off, you realize, oh, I'm just in a 0-dimensional vector space. So there is no modular form that could have been attached to this very strange elliptic curve. And because of how precise, how this modularity conjecture is stated, it implies that such an elliptic curve can't exist. And then that means that no such solution can exist to Fermat's last theorem. And that's roughly how it goes. And it's this modularity conjecture, a version of this is what Andrew Wells ended up proving with Taylor and Hill. But we now have a full proof of the modularity conjecture. But it's this close link which is somehow helped us do this. So modular forms play a key role in this. So this is maybe one of the interesting things to try and formalize, start formalizing. So let me start moving towards telling you the definition of this. So I first need some background stuff or some setup. So the first thing is modular forms are going to be functions from the complex upper half plane. So these are complex numbers which have imaginary part strictly greater than 0. And they're going to be functions from there to complex numbers, and they're going to transform under or preserve certain symmetries of my space. And these symmetries on the upper half space come from these what are called Mobius transformations. And they're given as follows. If you take a matrix with real entries and positive determinant, which I've denoted here by GL2R plus, then the Mobius transformation will take an element of the upper half plane, and it'll transform it to another element of the upper half plane by taking your matrix, say gamma, which you could write as ABCD, as I have here, and you send your point Z to AZ plus B over CZ plus D. You can check that this positive determinant condition means that this again lives in the upper half plane. And this allows you to move points from the upper half plane to the upper half plane. We call this an action on the upper half space. And as I just mentioned, modular forms somehow almost preserve this action. And let me make this precise. If you take the space of modular forms, so these are going to be functions from the upper half plane to C, we're going to have to satisfy 3 properties. The first one is this transformation property which I mentioned, and it's stated as follows. You take a fixed integer k, which we call the weight, and we take some fixed subgroup of SL2Z. These are the matrices with integer entries and determinant 1. And then we ask that for every element in this subgroup, you have this this condition. So f of AZ plus B or CZ plus D. This is what the Mobius transformation of the point Z was by my matrix ABCD. Looks like the value of f at Z up to this factor of CZ plus D to the K. Right here, K is my weight. If I wanted to maybe make the package this all up into one nice little definition, I could define the slash operator. So f slash K of gamma, this is the weight K slash operator by the matrix gamma, to be the function which sends Z to CZ plus D to the minus K times f of gamma dot Z. This is the action of gamma on the upper half plane. And then this transformation property just asks that my functions are invariant under this action. This is a right action of my group of matrices on my space of functions. And functions that satisfy this are called weakly modular. But for modular forms, we want a bit more analytic properties as well. So this is maybe like the algebraic side of the definition for modular forms. Analytically, one of the things that's important is that they are holomorphic on the upper half space. It'll turn out later that this is actually the condition which is the most annoying to work with when defining examples of modular forms, which are these Eisenstein series. But it's an important condition to have. And lastly, we have some conditions you can think of as being holomorphic at infinity. And roughly it says that, let me ignore this gamma and SL2Z for a moment. It says if you're high enough in the imaginary direction, so if you're above a point A in the imaginary direction, then the values of your function are bounded by some other point B. And we ask that this is true for every, not just for your function, but for every translate of your function by a matrix in SL2Z. Notice that, gamma is just a subgroup of SL2Z. So F weight, the slash operator by these elements won't be F again unless gamma was the whole SL2Z. So these are generally different functions, and I just asked that all of these are bounded as you go up to infinity. And these give you nice vector spaces. These we call this space of modular forms of weight gamma and level, of weight k and level gamma. And there's a nice subspace of this that we care about a lot, which are called the Cusp Forms. And you obtain these by changing this bounded at infinity condition for a 0 at infinity condition, which is quite similar. It just says for every epsilon greater than 0, if you're high enough in the imaginary direction, then you want the values of your function to be bounded by epsilon. So if you think of what this means, is you're just saying that the function is tending to 0 as you go up to infinity. And this is a nice vector subspace of my space of modular forms. And if you were just doing the theory, then it's not too hard to check that these things give you finite dimensional vector spaces. Although that's not something that we're going to show you. I'm not going to formalize that because the finite dimensionality is actually quite hard. It's quite a hard thing to prove, or at least we're still a bit of ways from it in Lean because we need more algebraic geometry for general levels, or Riemann Roch and Gaga and stuff like this. But I can show that there are.
Are we close to finite dimensionality, or is it miles away? Do you know?
I don't. I actually depends on how close we're to Gaga, I guess. And
I think we're a long way from Gaga.
Yeah, and Riemann Roch. I think for level 1, maybe we might be able to do it with this because it's just like some contour integral. But I was looking this up the other day, and for general levels or more general levels, if you want to write down like explicit dimension formulas, you really just need to use Riemann Roch and stuff. So I'm not sure. Feel well. So I won't tell you that they're finite dimensional, but we will define them to be complex vector spaces. And so let's start looking at how to do this in Lean. Luckily, Lean has this great method, so this library of mathematical results, and a lot of the required tools for defining modular forms are already in there. And for example, there's work of Alex, Heather, and Mark that they defined the upper half space. They also gave it the action by Mobius transformations, and they proved more that they proved what the fundamental domain for this action is, which is a really interesting, which is a really nice result. We won't need quite that much, but at least it's nice that we already have the upper half plane, we already have these Mobius transformations. I think they maybe defined it only for matrices in SL2Z, not for these GL2R+, but that extension isn't very hard to do. I think I just added that very, very quick. That was one of the first things I did. But the first thing we want to do is maybe define this slash operator, this slash k operator. And we do this as follows. So I want to define an operator on the space of functions from H to C. And this operator, it depends on two things. One is the weight, which is my integer Z in Z. And one is the matrix, my gamma, which is a matrix in GL2R+. So this is just the notation for in Lean for GL2R. And what I want to do is when I've given an integer and a matrix, I want to construct a map from this space of functions to itself. And if I were to ignore this Z bit, then I would just be, if you've seen stuff in Lean before, if it was just the last 3 arrows, then this would just be defining a has small, or using this to define a group action. In this case, technically it's going to be a right group action. I think lots of Lean's things are defined in terms of left group actions, but that's not a huge deal. But the problem is we have like an action parameterized by this integer k. So it's something you somehow got to extend this notation a bit more. And some people have had some ideas about to do this, but I've not yet implemented this. I just done this the most basic way, which is using this lambda notation. So I think that this is just a function, for me defining a function. And lambda says that here's a function which takes an integer k, a matrix gamma, and the function f, and it spits out a function on the far right hand side here, which takes element z in the upper half space, and it spits out f evaluated at the Mobius transformation of z by this matrix gamma. There's this factor of the determinant, which we didn't see above because all my matrices had determinant 1, but more generally one wants to put it in. Here, this gamma dot 1 just takes your matrix and removes the plus, so it just thinks of it as a matrix in GL2R, and then you just take the determinant of that. And that's just because the API for GL2R plus is yet to be completed, or there's more stuff that needs to be added there. So we can't define, I haven't defined a determinant on there just yet. And then lastly, you have this term here, this gamma 1, 0. This is the 1, 0 entry of your matrix. So it's like your C. z, and then just gamma 1, 1 is your d entry. And then this is the power k to the minus 1. And this is the almost the same definition I gave you up here for this measure. This is this definition here, apart from this factor of the determinant you can't see. And then using this, we can define the vector subspace of functions which are weakly modular. In Lean, you can define submodules using this a structure system. So you have a module which you want to think of this as your parent module, and you want to construct a submodule of this. So you're just required to give what the word sub is. So I want the functions from the upper half plane to C such that they satisfy some condition. And here my condition is what you expect, that for every element of my subgroup of SL2Z, this is what my gamma is, I have that the weight K / action by this matrix, now thought of as a matrix in GL2R plus. You have some coercion between matrices or subgroups in SL2Z into GL2R plus. We asked that these functions are, this function is the same as my original function, so that my function is invariant under this /k weight action. And one thing to know is that Lean already knows, for example, that the space of functions from the upper half plane to C is a complex vector space. So that's quite nice. All I need to now prove is just that I have a sub-vector space for this. So I just got to give it what the sub is, and then these dots here just mean the extra proof term. So you want to give it the proofs that it actually is a submodule. So for example, if you add two things, they stay inside your submodule. If you do like scalar multiplication, it stays in your submodule. And I think if you like act by 0, it's trivial or something. I can't remember the last one. But this defines your vector submodule. Think of vector, if not seen this before, it's just a vector space. So this is a complex vector space of functions which are weakly modular. So that's the first thing we have. And this one was pretty easy. And now I start looking towards the holomorphic condition, which is the next one. Now, there's good things and bad things about this. On the one hand, we're lucky because there's lots of different ways to define holomorphic in Lean. But on the other hand, we're unlucky because there's lots of different ways to define things in Lean, meaning that we have to choose which one to work with. And in this case, there are several, but let me highlight two, which are maybe the most natural to try. The first one is this differentiable on, which tells you when a function between normed vector spaces is differentiable on some subset of its domain. And it's just, remember, holomorphic just means that for every point in this domain, there's a little neighborhood where you have a derivative. And this is great because a lot of the recent results of complex analysis that have been added to the math library are stated in terms of differentiable on. So if I want to use like lots of this high-level complex analysis, which I'm going to end up needing for proving the holomorphicity of my Eisenstein series, this is a great definition to work with. But unfortunately, I can't use this directly for my modular forms because this upper half space is not a norm vector space. It's not a vector space because if you multiply by -1, you move out of it. And you could cheat, for example, you could extend your function from the upper half plane to C to functions that come from the complex numbers to itself by just saying, well, it's extending your function by 0. And this works. Most of the actual proofs for holomorphicity later on actually secretly are doing this at the moment because, well, I just wanted to do it and not do it very prettily for starters. But once all of this gets PR'd, it have to be a bit more intrinsic. But there is a nicer way of defining differentiability or holomorphicity, and it's this M differentiable. So I think M stands for manifold, and this tells you when a function between two manifolds is differentiable. And this is great because somehow this doesn't rely on me extending my functions arbitrarily. I can use this option to just say, well, when a function between the upper half space and the complex numbers is differentiable. But now I need to think of the upper half space not as a subtype, not as a set of elements whose imaginary part is greater than 0. I got to think of these as a complex manifold. And so essentially, I want to create a complex manifold out of the upper half space. And you can do this because Lean, for example, already knows that the complex numbers form a complex manifold. That's easy. And it also knows that open subsets of manifolds are manifolds. So if I can just check that the upper half space is an open subset of complex numbers, I can automatically infer that that is the complex manifold. And this basically means I need to write my upper half space as an element of type open subsets of C. So I need to take my upper half space and add a proof to it, which says that it's open in the complex number with the normal topology. And this isn't hard, but I want to give this a new name. So when you see H prime, this is what this means. This means now the upper half space are now considered as a complex manifold. And there's some slight nuances to this, but now I need to take my functions, which are from the upper half space to C, and somehow coerce them into not making them functions between manifolds. But this can work. This isn't so bad. And before I give you the full definition of modular forms, let me just show you that quickly the is bounded at infinity and is zero at infinity conditions. These two conditions, I think before I had A's and B's, and here I have M and A's. I can't remember why I forgot to change it. But you can see this is a nice example of the lean code looking almost exactly like the math code that you'd have. Maybe the arrows, maybe this arrow here is maybe something you wouldn't write math-wise, but this is just an implication of what you're expecting, what you're trying to define. This is quite nice. A function, you have some real numbers such that if you're high enough in the imaginary direction, then the absolute value is bounded by n. And similarly for your zero and infinity. If you put all of this together, you can define a modular form as a structure. So I want to define when when a function between the upper half plane is C and the complex numbers is a modular form of level gamma and weight k. So I give it my level and my weight and my function, and I want to satisfy some property. And this property is, well, some prop, and these are three things. First of all, that it's Hol stands for holomorphic. So I want it to be M differentiable, so manifold differentiable. Let's ignore these two terms for a second in the middle. And I want it to be as differential now as a function between H primes and C. So it's a function between manifolds. And this is what this upper arrow here does. It takes my function between the upper half space and C and coerces it into a function now of manifolds. And these J's of C's, the first one is giving the H prime, the structure as a complex manifold, by inducing it from the structure of C as a complex manifold. And the same thing, this J of C is giving the complex numbers the structure of a complex manifold. I think this stands for model with corners. But this isn't something too much to worry about. This is just differential between these two manifolds. Great. The second one is being this transformation property, my symmetries that I care about. And this just means that I want to be a member of this weakly modular submodule that I define. So I want it to be part of this module of functions which transform nicely under the slash operator. And lastly, I want my bounded at infinity condition, which I remember Carl said for every matrix in SL2Z, I wanted something to hold. Because I've conditioned over subgroups of SL2Z, I can't just write SL2Z. I got to take SL2Z as a subgroup of SL2Z. So this is what this T means. This is the top subgroup. This is the largest subgroup of SL2Z, which is isomorphic to SL2Z, obviously. But Lean makes this distinction. So that's why it's this top here. And I just ask that this transformation is always bounded at infinity, just as we had before. And you can do similar things, changing this last condition for zero at infinity to get your spaces of Cusp Forms. And you can check easily again, because of how I define all of these things, that this actually forms a complex vector space. And I just do the same thing. It's just it's a structure to define a submodule. I just have my carrier again. Now it's just that it's a modular form of weight gamma and level k. Sorry, I said that again. Of level gamma and weight k. And then a bunch of proofs that it satisfies the properties, which are of being a submodule, which I again suppressed from my slides because they're not very interesting. And this all again works with the Cusp Forms exactly the same. You can check that Cusp Forms are subspaces, which is nice. Now, before going on, let me just mention some common types of levels of these modular forms. Usually, we don't just care about any modular form. We care any level. We have some like preferred ones that we like. And because this will show up later, I want to highlight them here. First of all, we have gamma naught n, given n some natural number. Gamma naught n, you can think of these as a matrix, so when you reduce mod n, they look upper triangular. Full gamma n, this one at the bottom just looks like matrices, such that when you reduce mod n, they look like the identity. And gamma 1n is something in between. It's the ones where when you reduce mod n, the bottom row looks like 0, 1. And these are nice subgroups to work with. The modularity conjecture later is going to be stated for modular forms of level gamma naught n, which is why I like to mention them here. And all of these things have been formalized in Lean. I formalize them as well, including like the definition of being a congruent subgroup and a few basic properties of congruent subgroups. But this isn't very hard, this stuff. This is just the matrix and group parts of MATLAB are quite well developed. So this is pretty easy to do. So let's start looking at some basic examples of modular forms. If you pick up any book on modular forms, the first thing you'll see come up are Eisenstein Servers. Now, they're defined quite simply. It's like almost some averaging process. You want to sum over all pairs of integers, c and d, not both 0, and take 1 over cz plus d to the k. And it turns out that this sum for k large enough defines to you a holomorphic function, which is actually a modular form. And it'll be a modular form of level SL2z. And for k, which are even and greater than 4, you can actually check that these things are non-trivial. And this is quite nice. So this is what we wanted. This is the examples that we want to do. I wanted to do in Lean, because this is like, well, I didn't want to have just the 0 function as an example of a modular form. I wanted something more interesting. So this is what this why you want to do Eisenstein series. And this definition to formalize it is not very hard. Just the definition of this function. You just do this in 2 steps. The hard bit is going to be proven that they're holomorphic. The first thing is I defined this Eise function, which is short for Eisenstein, and given some integer and some element of the upper half space, it's just a map from z squared to the complex numbers given by sending x, think of your c and d, and sends it to 1 over x dot 1 is your c times z plus x dot 2, which is your d, all to the power k. And notice I didn't have to worry about dividing by 0 here at all. This is something common in MATLAB. You don't want to condition on your definitions. And in MATLAB, 1 over 0 is just defined to be 0 for the complex numbers. So this wouldn't be an issue anyway. As long as you're not allowed to say 0 inverse times 0 is 1, then everything works out fine. So there's no contradictions. But this is nice. I don't have to worry about dividing by 0. And I just want to define my Eisenstein series to be the sum of these functions. So Eisenstein series of weight k is a function from the upper half space to c, which is given by the lambda. So lambda is a function. Z goes to this primed sum. I'm going to do this in a second. Over all pairs in z cross z of this function that I defined above. Now, the primed here doesn't denote the pairs which aren't 0, 0, because I just told you I don't need to worry about that. Here, primed stands for T-sum in Lean, which I think is topological sum. And it allows you to define infinite sums inside of topological monoids. And it's defined in such a way that if my the sum that I'm trying to do converges absolutely, then I get the right answer. Otherwise, it just gives me 0. And turns out that for Eisenstein series, if k is greater than 3 or greater than equal to 3, then these will be absolutely convergent series. So this will work out perfectly fine. This is one of the things we'll check later. And this definition has some like perks, but also some drawbacks. If I were to plug in the number 2 for my weight, then this is still an interesting function mathematically. It's not a modular form. It's not a modular form because it doesn't converge absolutely. You can check that it doesn't transform properly. But how I've defined it, because this doesn't converge absolutely, this function in my definition, if I plug in 2, you just end up working with the function which is just the identically 0 function. And the 0 function is a perfectly good modular form. So using this T-sum definition, whilst I can't quite define this function, I'll have to think of something else to define in G2 later on. I can check that my Eisenstein series are all weakly modular, for example, for any weight k, which is a nice little perk. Just because as soon as k is something is 2 or anything less than 2, this sum isn't absolutely convergent, so you're just working with a zero function, and the zero function is weakly modular. And to check the weakly modularity, there's two steps. First, you just check how this Isaac function, this little component functions, transform under the action of Mobius transformations. So this is what this first lemma says. If you look at the Isaac function evaluated at the Mobius transformation of z at C and D, this is what this I stands for your pair of integers, then you just get your CZ plus D thing here times the value of the Isaac function. But now you've permuted the indexing set over which you're working. And if you remember from basic analysis, absolutely convergent sequences, it doesn't matter in which way you order the indices, which in lean basically turns into saying, it doesn't matter if I transform my indexing set, of which I'm summing, if I move it under an equivalence, so I think of a permutation, then lights gone off in here, then the value of my function is exactly the same. And so this indiquiv, this is just an equivalence from z squared to z squared given by a matrix in SL2Z. I won't say it here, but yeah, it's an easy equivalence that you get once you work out the linear algebra, or you just do the algebra. And so combining these two things, you just get that you can just show using this result and properties of this topological sum that Eisenstein series are what I call doubly modular, weakly modular for any subgroup and for any weight k. And so that this is the lemma that I proved. All I should say now, everything else, all the lemmas that I show have sorry-free proofs. There is a pull request where you can find all this code, or I have a repo if you're interested. But everything I'll show, other than the modularity conjecture, that one's not sorry-free, unfortunately. Everything else is sorry-free. Although at the moment, a lot of the proofs are very ugly. They're not been golfed or anything, but at least it works. So we can check Eisenstein series are weakly modular. Nice. So now let's start working towards the harder bits. One thing to notice is that I didn't even need to talk about things converging absolutely or uniformly. And this was great from weak modularity. I didn't need to do this, but I'm going to have to prove it eventually. And it's going to come into my proof of holomorphicity now.
Oh, wait, you didn't even assume it converged?
Yeah, assume it well, because otherwise you just get the zero function, and the zero function just works perfectly fine. So you don't need to assume anything, which is nice, yeah. But for the holomorphicity, then yeah, it's going to come and collect. You can't get away from it. And how you want to do this is you want to rearrange your sum, defining your Eisenstein series, and then check that you can write as a sum of functions which are holomorphic and converge uniformly. And they won't converge uniformly on the whole upper half space, but I'll slice it up into little pieces where it works, and then we'll somehow glue our ways up to the full result. But the basic idea is somehow as follows: I take my GK, this is my Eisenstein series, and I write it as a sum now indexed over the integers of these functions GKN, which is this Isaac function which I had 1 over CZ plus e to the k. But now I'm summing over what I call Sn. This is think of this as a square in the lattice Z cross Z. These are the elements in Z cross Z such that the maximum of their absolute values is exactly n. And you can define this set, this finite set in lean. One of the annoying things is checking that it's, well, we need to know more than it's just finite. We also need to know that exactly how big it is. And it turns out this set has size 8n for n not 0, and obviously n some positive integer. But proving that is like fiddly, as with most things. Trying to prove cardinality of sets or thin sets in lean at the moment is a little fiddly. So the proofs of this are really, really ugly. So I wouldn't dare look at them. But you can do this. Once you've rearranged your sum into a sum of GKNs, then what we want to show is that not only that the full sum of the sum defining that the Eisenstein series converges absolutely, but that the partial sums of these functions converge uniformly to GK. Let me show you a bit of how you do these two things. So the first thing is this absolute convergence. Absolute convergence in lean is called summable. So you want your sum to be summable. And this just says that all of these Isa functions, if I take the sum over all their indexing sets, or over z squared, I get a absolutely convergent series sequence when my weight is at least 3. And you can prove this on basically directly, that it relies on bounding your Eisenstein series by the Riemann zeta function and some explicit function that you can write down. It's a bit fiddly, but it works. I don't even need to split up my upper half space into slices for this. This works quite nice. But the next thing we want is that these functions, these GKNs, I want them to converge uniformly to my function, to my Eisenstein series. And for this, I really do need to now split up my upper half space into those slices. So I define this HAB. So these are the set of elements in my upper half space such that the width of my integral is bounded by A, and it starts above B. So the x values is less than A and the y is greater than B. So it's like, think of it as like a little slice that goes up to infinity. And on each of these slices, you can check that this partial sum of functions, when restricted to this slice, converges uniformly to the Eisenstein series, also restricted to this little slice. And so this is what this lemma is saying. That if I have k greater than an integer greater than 3, I have my slice of the upper half space actually in the upper half space. So this is why a greater than 0 and b at least, sorry, b strictly greater than 0 because I want my slice to be in the upper half space. Then tends to uniformly is just the statement that a sequence converges uniformly. And this is here for this you need your functions to all have the same domain. So which is why I need to restrict all of my functions to this upper half space slice, as I call it. So this Eisenpar sum slice is just this partial sum restricted to the slice defined by A and B. And Eisenstein series restrict KAB is just the restriction of Eisenstein series to this slice as well. And you just check that these things converge uniformly. You can write down a bound, and then you just use the Weierstrass M test to do this. I have a very basic version of this Weierstrass M test, but recently Heather Macbeth has added like a proper version of the Weierstrass M test, which mine was just stated for complex functions, but this one works a lot more generally and stuff. So when this actually gets PR'd, there'll be a much better proof of this in the library. But this is fine. This is still not the hardest bit that you need to do. The hardest bit is the holomorphicity. The idea is because I've rewritten my sum of my Eisenstein series as an infinite sum of functions, each of these functions, these GKNs, this is a finite sum of holomorphic functions. Because I was adding over this set Sn, which has size 8n. This is a finite set. Each GKN is a holomorphic function, and I now have a sequence of holomorphic functions converging uniformly. And this result that I've written down here says that if you have such a sequence, then the limit function to this will also be holomorphic. And this is what you want to use. First, while I thought about trying to do this directly, trying to just cheat and try and prove the holomorphicity direct to Eisenstein series, but you can't do this. I hadn't seen a proof like this in the literature. I think there's a reason for this. You really need to use complex analysis for this. And the missing piece for this, which basically quite recently been added by Yuri, was this theory of complex analysis, these Cauchy integral form. You really needed this to be able to do this this result. And basically the idea, let me show you what the idea is to prove this result. What you do is, because each of your functions is holomorphic, then Cauchy's integral formula says that if I have a holomorphic function, then if I choose appropriate little disks, I can write this function, the values of this function, as the value of some function defined by an integral. Here I have the integral over some disk of my function divided by zeta minus w, which if I were to write out this integral over a circle and parameterize my integral, then it turns into this thing on the right, which is why I've written it out like this. This is what Lean thinks a circle integral is. And so if your function is holomorphic, you have this equality that you have here. And now, if my functions are converging uniformly, then this Fn is converging to an F down here, and this integral converges to an integral of a function. And this is the first thing you need to prove, that you have these, that the uniform convergence implies a convergence of these functions defined by integrals. And then once you know that your limit function looks like the function defined by an integral, you just check that this function is differentiable by basically differentiating under the integral, which is another thing you need to prove. And so the Cauchy integral formula was a big thing we needed for this. This result that the uniform convergence implies the uniform convergence with the integral, so that you can basically swap the limit and the integral. That we had some versions something that we could use for this, but it wasn't quite stated in the right version. And this differentiation on the integral, we had a super general version of this already in MathLib, but it had a lot more of hypotheses. So in order to do it in this case for complex functions and stuff, it's still a bit of annoyance to prove it, but the framework was there already. And I should just say, because holomorphicity is a local property, this set S here, it says sequence of functions on some open subset. If it converges uniformly, then on every complex subset of this, then you get a holomorphic function. And because this holomorphicity is a local property, I can always take my S's to just be some balls, so like some closed balls or open balls. And so this is what you'll see stated in the code that I'm going to show you in a second. So yeah, the first thing, as I just said, is integral consequent of Cauchy's integral formula, which Yuri has added. But using this, this is me to show you what a version of Cauchy's integral formula looks like, which I've just written out. So I've taken a function, and I picked up some small ball over which I wanted to talk about. And I said, has Cauchy integral form? I just say, if I have a differentiable function on a closed ball, ignore most of this stuff, then the values of this function on elements inside this ball, it just looks like this expression 1/2 pi I integral. So this is what this whole horrible expression has here. But this is one version of what the Cauchy integral formula looks like. And this is exactly one of the things that Yuri added. Although now we have better notation for this. We actually have circle integral notation, so it doesn't look as ugly as what I've written here. But the next thing you want to do is the statement I said that if my functions converge uniformly, then the integrals of these functions converge to the integral. Also converge. And this is what this lemma int uniform lim of int says. I'll think of a better name for this later on. Ignore most of the stuff in here, but most of this stuff is just telling me what balls to work on. But roughly, this is just stated. At the moment, it's not very general because it's just the case that I needed, but when all of this gets PR, I'm sure it'll be super general for general variables and stuff. At the moment, it just says if I have a sequence of functions, so for every n of n, I have a function from the complex numbers to complex numbers, and I have my limit function, c to c, and such that every one of my functions is continuous on a closed ball, and the limit of my sequence of functions is my little f, so this tends to uniformly on f. So it says that this sequence of functions converges on this closed ball to my little limit function f. Then the limit of the function defined by the integral, this is the function that says lambda to the integral from 0 to 2 pi of this Cauchy disk function, whatever this is. Cauchy disk function is just this parametrized version of the integral, this horrible expression that I had before. Then the limit of these, the integrals of these fn's tends to the limit of the integral of my limit function, my little f. And yeah, so you can do this. It's not too bad, but there's a little bit fiddly in some places. But it works. This again is sorry free. And the next thing you want is this statement, which I said that if I had a function defined by an integral, then I could differentiate this function. And as I said, this was defined more generally. There's more general ways of doing it, but here's like a version that we proved, or that I proved, which I called Cauchy disk form is differentiable on. It said if I have appropriate disks for a function which is continuous on the closed ball, then this Cauchy disk form, this is just the function defined by this integral expression here, that this function is differentiable on the complex, differentiable as a function of complex numbers and it's differentiable on some open ball of radius strictly smaller than the radius over which this you're taking the integral on. And this is enough. These two functions, as I said, all of these closed balls, by localizing, this will be enough to glue together to get the full result. These two results together give you this. Uniform of diff is diff. So if I have a uniform limit of differentiable functions, so each of I have a bunch of functions fn, such that each of them is differentiable on some closed ball, and they tend uniformly to a little function f at the end at the top inside of this closed ball. Then by limit function f is differentiable on some ball of strictly smaller radius. And you have to be careful with, you don't want to make sure you want to make sure your radii are negative. So there's these extra funny little conditions here just to make sure that the balls don't have negative radius and stuff like this.
I think one of your conditions implies another, right?
Probably, yeah. It's just at the moment I've not I've not gone through to try and PR this, so yeah, I wouldn't be surprised if that's the case. But this is a very local version of this uniform limits of holomorphic functions is holomorphic. This is say just for little disks, but from this you can just build it up to the statement that you want for modular forms. And in particular, you can, using this, you can prove that Eisenstein series are manifold differentiable. So you can take this Eisenstein series and using this, the fact that I already knew I had that on every little slice of my upper half space, I knew that I had a uniform limit of functions which converged to my function, and all of these functions were holomorphic. I can just, working slice by slice, you basically glue it all together and you get this this result.
So this is absolutely fabulous. I mean, this is something that was just inaccessible a year or so ago, right? How long is the code?
Oh, it won't be as long as it is now once it's PR, that's for sure. It's quite long, but it's mainly because I wouldn't say how, I want to take that as a measure of how complicated it is, more of a how bad I am at lean.
This is how you learn. You should see my 200-line proof the square root of 3 is irrational that I wrote in 2017.
Yeah. Okay. Yeah. Well, there's something like this. The files at the moment is quite huge just because my proofs are very bad and very slow. The two basic steps of commuting the limit, well, not quite commuting, but the limit and the integral. That statement, we weren't too far away from it in lean, but still needed to take the super general version and apply it to this case. And this differentiating on the integral, again, we had a very general version, but specializing it to this case took me longer than it should, but I think that's just my fault. And then there's Yuri's Cauchy's integral formula stuff. That is quite a lot of lines of code, but those are actual important. That code is already quite well golfed and stuff, so maybe that's a good indicator of how hard this was, that we needed all this Cauchy, this complex analysis to do it. And so yeah, you see, and here, crucially, k is greater than 3. So all of the conditions here, I do use condition on my weights, which I didn't use when I was proving holomorphic weak modularity. Now, what remains is to check that these functions are bounded at infinity. This actually uses that function is weakly holomorphic, and it also uses absolute convergence. And I won't go into the details of this, it's not too hard, but the idea is, because my function is on the upper half space it's a function of level SLTZ, it means that if you plug in the matrix 1, 1, 0, 1, you'll see that these functions have to be periodic. So f of z plus 1 has to be the same as f of z from Eisenstein series. And that basically means I can just, it doesn't matter how far I translate to the left or right on the upper half space, I can always, translate my function so that I'm just working on one of these little slices of my upper half space. And now every one of these little slices that I have, I know that I have a absolutely convergent sum which converges to my Eisenstein series. And the way I prove this, I was using the Weierstrass M test, which relies on bounding your functions by some uniform bound. And essentially, the proof of the absolute convergence, you just rewrite it, and you get that on each of these little slices, your function has to be bounded at infinity. and just by translating your function along as far as you need, you put it into one of these slices and then you're done. Maybe that didn't make too much sense, but basically you use a weak modularity to move yourself into a nice slice of your upper half space, and then you just basically use the proof of absolute convergence to get yourself the A's and B's in the definition of bounded infinity. And because I'm using absolute convergence in my thing, this is again the k greater than 3 is coming into this proof. So this is again conditioning on how big my weight is. And if you put everything I've said together, you get something like this. This is what looks like what at the moment is what the proof that an Eisenstein series is a modular form. This is what it looks like at the moment in Lean. It's not very well golfed, and I've somehow written it out here to try and split up the 3 different bits. But this says an Eisenstein series is a modular form for k, some natural number of at least 3, and it's a modular form of level, the top subgroup of SL2Z, so level SL2Z and weight k. And the holomorphicity is this function, this result I showed you before, Eisenstein series and diff. Here you can see that it depends on the weight, k being greater than 3. The transformation property, it being weakly modular, it's just this result that I showed you before, which only depended on, it didn't depend on k being greater than 3 or anything. And then this proof at infinity, which is a bit of a mess at the moment, but it's essentially this thing that I said. Once you know the function is weakly modular, you just translate it. You can translate it into a slice, and then on the slice we can check that the function is bounded. And again, you have this HK hypothesis showing up, so you really need it. And this gives us R3 proof in the code that I have right now. So that was nice. But as soon as I did this, I realized, our Eisenstein series is non-zero, and I've not told you that they're not zero. They're not identically zero function, and this is something that I've yet to prove. So these are interesting examples, and we know that they're not zero. But the proof that Eisenstein series aren't zero is actually a little bit more annoying than I thought it would be, in that we still need a few more analysis results to be added. They're not very hard ones, but it's just some basic ones, which maybe they're there by now, but I couldn't find them. You need something like you need to bound, for example, a sum of functions by an integral and stuff like this, and this integral comparison test, I think is what it's called. That's something that's needed. But this is very, I said words integral comparison test, and to me that scares me, because I think of like cohomology or something. But no, this is like basic analysis. I need to bound a sum by an integral. That might be already in Lean, but I couldn't find it. So this is one of the ways to check that. For example, G4, the function when you put weight 4 in, that if you plug in, ask for the value at I, square root of -1, that value is, you can check that value is non-zero, but you need to somehow bound up the size of a sum and stuff like this, which is fiddly to do in general, or in Lean at the moment. So, but hopefully I'll add that soon. It shouldn't be too hard. Other things to do is I've not given any examples of Cusp forms. I can define a function which will end up being a Cusp form. You can take a linear combination, but if you take like G4 cubed minus E6 squared or something, divided by 1728, then you get delta, which is the discriminant function.
Have you proved the product of a form of weight k and a form of weight L is a form of weight k plus L?
Yes, that's that. I was trying to make it into a graded ring, but when I was doing this, I got confused about how the graded ring API was working, so I haven't actually got that bit, but I can prove that the product, I think I have all the ingredients. I just need to get to understand the graded ring API a bit better to actually prove that.
Yeah, it is a bit of a minefield.
Yeah, it shouldn't be hard, but it's all there. It's just I need to figure out how to do the structure properly. Anyway, but yeah, so I could define a function which I would then have to check is a Cusp form, so I need to check it 0 to infinity. And the best way of doing this is working with Q expansions and stuff. And that we still don't have that. We need a good theory of Q expansions to actually start understanding these modular forms. Q expansions, remember, I should get to start with these Fourier expansions for my holomorphic functions. And then we want to just start doing interesting things about modular forms, like defining Hecke operators. All of this has been done with Hecke operators in mind. I have some other PRs defining like double cosets and commensurability and stuff, so that we can define Hecke algebras, and eventually hope to define this like Akinlena theory. And, it'd be nice to prove like multiplicity one and stuff. And then eventually, in like 100 years, we'll have the modularity conjecture and Fermat's theorem all formalized, but still a ways from that. But I can state the modularity conjecture, and this is what I'm going to do now in just the last few minutes. I never told you exactly what the modularity conjecture said, so let me first start by telling you what a statement of the modularity conjecture. And to do this, I need to define an invariant of my elliptic curve. And in Lean at the moment, elliptic curves are just defined as they're given by a set of 5 numbers, A1, A2, A3, sorry, A1, A2, A3, A4, A6. These are the coefficients in a generalized Weierstrass form. And they're numbers like they're these 5 numbers with the condition that the discriminant of this cubic that I have here is non-zero. And this is at the moment all that we know about elliptic curves, as far as I can tell in Lean. But given an elliptic curve, we want to define the APs of E. And this is defined as P minus the number of solutions that your Weierstrass equation has with mod P. So you want to think of reducing your equation mod P, and then you count how many solutions this has over FP. And then AP is just the difference of P minus that. And if you've seen this before and you're thinking this is a little bit weird, sometimes it's a P plus 1. Notice that I'm not thinking of my elliptic curves as having a point at infinity with this definition. So there's no point at infinity that I need to. So this MP of E doesn't count the point at infinity. So I don't have to take an extra point. I don't have to do a P plus 1 here, which is maybe the more standard way of saying this, this quantity defined. So we want to define this in Lean. Oh, so I'll get to that in a moment. But with this quantity, AP of E, the one version of the modularity conjecture says that given an elliptic curve over the rational numbers, so these AIs are rational numbers, there exists some natural number and some modular form of weight 2 and level gamma naught n. So when I talk about, I mentioned my levels briefly before, such that for every prime not dividing this element, this number n, we have that the APs of E's look like the P Fourier coefficient of my modular form. And this turns out to have lots of alternative versions of this same statement, which look quite different, but this is equivalent to that statement. One thing to note is that I had to add this P not dividing n thing because I've not talked about primes of bad reduction for my curve or define the conductors and stuff like this. So you can somehow get an equivalent statement by just doing this. It basically guarantees that when you reduce mod P, you do end up with a nice equation that you want to work with. But this is what the math version of the modularity conjecture, or the Shimura-Taniyama conjecture, as sometimes known. And we want to formalize this. And one thing that we're going to need, I'm mentioning here, are Q expansion coefficients on a modular form. And I've not told you anything about Q expansion. I just said before that Q expansions is something that I want to add later on. So how do you do this? Well, there's a cheat, right? There's a nice little lemma which says if I have a modular form of weight k and level gamma naught n, it has a, say, and assume it has a Q expansion of this form, a and f, q to the n. Again, q remembers e to the 2 pi I z. Then just from this expression, you can pick out the Fourier coefficients by just doing this integral here. So I can define my Q expansion coefficients just by this integral expression here. And so, I forgot, there should be a space there, I'm sorry. So we define a n of f in Lean as, so given a modular form an, so this is modular form under bracket an, the an of it, given a modular form of level gamma naught n and weight k, I define a complex number. This is going to spit out an integral. It's going to spit me out a complex number, and given by the integral from 0 to 1 of this expression. Here, this f dot 1 means that I've taken my modular form. Dot 1 makes it think of it just as a function, and the map to upper is just a function that takes an element, a real number, and it adds I to it, so that it becomes an element of the upper half space. Because the upper half space is defined as it's a type, so it needs to be a complex number together with a proof that its imaginary part is greater than 0. So you actually need to prove that. You got to give it x plus I and prove that x plus I has imaginary part greater than 0. So this is just technical nonsense. But this gives you the Fourier coefficient for modular form. The APs of your elliptic curve I define to be basically, as I said before, p minus the cardinal. So this is the size of the set of points that my elliptic curve has mod p. Cardinal just gives me attaches a cardinality to a set, and this 2nat attaches a natural number to the cardinality if this cardinality is finite or non-empty. So if this set is not empty, then it would give me 0. If the set was infinite, it would give me 0. But if it's a finite set, it will give me the right size. And this set of points mod n is just what you get from, it's a number of points which satisfy this giant equation, this giant cubic. So I have the points in z mod n cross z mod n such that the equation is satisfied. And this red that you see here, this is just me reducing the coefficients on my elliptic curve mod n. And these are rational numbers which I'm reducing mod n. So I just, you define it with the usual cheats in Latin, which you say, you're allowed to divide by 0 because 1 over 0 is 0. So you can just define, you take the numerator and denominator and reduce each of them mod n, and just one divided by the other works fine. And in this p not dividing n, this will take care of making sure that and I'm actually not dividing by 0 later on in the statement of my modularity conjecture. And one thing to notice, that this is very bad. I've done very bad notation here because my elliptic curve dot AP, that means that if I take an elliptic curve and I do ask dot AP of p, that'll give me this definition of the AP of E. But then also the coefficients defining the modular form are defined by, are called A1, A2, A4, A6. So for example, A3 is a pretty bad one because this is the A3 defining the bias equation, but also it was A3 comma 3, and this would be the third number of points elliptic curve has over F3 of them. So I'll have to change that notation later. But put it all together, here's a proof of the not proof. Here's a statement of the modularity conjecture. So given elliptic curve over Q, there exists an n in a modular form of level coming out n and weight 2, such that for every prime p, such that p doesn't divide n, we have the p Fourier coefficient of a modular form looks like the AP of E of my elliptic curve. And here's, I guess, a joke. It's not actually this simple. Simp doesn't actually work. I tried this to see if it would work, but it doesn't. So that's unfortunate. But yeah, this is a basic statement of the modularity conjecture. And that's everything I have to say. So I think I'll leave it there. Thanks for listening.
Well, thank you very much.
All right.